Now we're going to move on to Chapter 6S, which is the supplement to Chapter 6. So after you read Chapter 6 on quality management, then we're going to move to Statistical Process Control, which is Chapter 6S. Our learning objectives for Chapter 6S are explain the purpose and use of a control chart. We're going to learn how to build X charts, R charts, P charts, and C charts. We're going to learn how to build a control chart with all the various steps that you need. We're going to learn when to use which kind of control chart, and then we're going to explain process capability and compute our CP and our CPK. Before we dive into statistical process control, we need to talk about what quality control is and understand, how are we managing quality in a manufacturing or a service setting? Well, quality control is ensuring that a good or service conforms to the specification and meets the customer requirements by monitoring and measuring processes and making sure any adjustments to maintain a specified level of performance. So we're going to monitor and measure the products that we make to make sure that they are meeting our requirements, and if they are not, then we will make adjustments to that production process. Quality control systems have 3 goals. That's to perform a standard or a goal. So we want to get to a specified performance level. We've got to have a means for measuring our actual performance. So if you recall earlier when I was saying all those different sayings, you can't monitor what you can't measure. So you need to have a means for measuring actual performance. And comparison of the actual performance with the standard to form the basis for corrective action. So you need to be able to know your comparison of your benchmark of your actual performance so that you can actually do corrective measures. Quality at the source is the people responsible for the work and the quality of their processes by identifying and correcting any defects or errors when they are first recognized or occur. So we have talked about employee empowerment. That requires that employees have a voice, that they can speak up when they believe something is going wrong at their workstation, or they are collecting data to provide to upper management of the observations that they've got. So your employees have to be properly trained, they've got to have the right tools, and they've got to have the support of management, and they can generally help to improve quality at the source of their place of manufacture. When you're closer to an error, it's easier to fix it right then and there. So one rule of quality control is the 1-10-100 rule. And this is a lot like the slide that I showed you in when we were talking about the costs of quality. So I was showing you that there's the appraisal costs and the prevention costs, internal error costs, and then external error costs, and the difference, how much those costs can cost an organization depending on when they are found in the life cycle of that production. Same thing here. So good quality control, it costs you $1 to fix an error at the prevention or the appraisal cost. So fix and find errors during design costs about $1. Then if you move on and fix and find quality errors during the production process, it costs about $10. So that would be an internal failure cost. You're finding that something is wrong while you're manufacturing it, so you fix it before it ever gets to your customers. And then with the 1-10-100 rule, you can see that at the very top here, when you find and fix an error out in the field, that's the equivalent of your external failure cost. So with quality control, you want to try and catch problems as early as you can. You want to improve quality at the source so that those defects do not make it out of your facility. Otherwise, the cost ratio is dramatically higher. So it multiplies by 10 as you go further and further along in that production process. So quality control practices. In manufacturing, there's lots of things you can do to improve your quality and improve your quality control practices. The very first thing you can do is work with your suppliers and make sure that they are certified, that you're monitoring them, so that when they deliver products to you, that those products are good and that they're high quality, that they're not failing upon receipt. So supplier certification and management is a great way in manufacturing to make sure that the products that you get are high quality. For the first 7 or 8 years when I worked in manufacturing, I worked at a place that did a lot of inspection. They did incoming inspection, they tested sampling of the parts received from their suppliers. Then they did testing during the production process at various different stages as that product was being built. Then they did finished goods inspection, making sure that that product conformed before ever sending it to the finished goods customer. Well, the next manufacturer that I worked at didn't do a whole lot of incoming inspection. And so they had, 5 or 6 less people on staff who were not just inspecting parts upon receipt. And their philosophy was that they would rather have supplier quality engineers who picked really good suppliers, managed those suppliers, and then audited those suppliers at their manufacturing facilities versus having incoming inspection. And so we had 1 or 2 supplier quality engineers versus 5 or 6 or however many incoming inspectors that we had, and they skipped that step of inspection because they built quality control practices into their supplier management system. So it was a change in mentality for me, but I really liked it. I appreciated it. And if there ever were problems in that manufacturing process, they still caught them while they were manufacturing the goods. So they caught them in the internal process because they did inspection on the production line. So they still never got out to the customers, but it was just a mentality shift for me. So you can do in-process control that makes sure that the products that you're building don't leave your facility if there's any quality issues. And finished goods control, most places do that. You'll see, inspected by or tested by, inspector number 3 on a lot of the products that you buy. They've got little stickers on there that says they did a finished goods control prior to shipping those goods to you. Quality control practices and services. We went over in the last lecture recording what a poka-yoke is. It's creating error-proof processes so that those mistakes can't happen. There's lots of things you can do in service to make sure that you are still following a check sheet and doing all of the different processes that you're supposed to have a high-quality service output. So an example that came to me when I was thinking through this lecture is I got my oil changed about 2 weeks ago. And these guys had a checklist that they went through one by one, and there was another person there, doing it with them. So they said, checking his blinkers, check, checking his brake lights, check, turn this on, turn that off, press this button. And they were working together and they went through this checklist. So they were making sure that they were following a quality control process for that service. So whether it's manufacturing or services is irrelevant, you can build quality control practices into whatever that you do. Okay, so statistical process control, that is a methodology for monitoring quality of manufacturing and service delivery processes to help identify and eliminate unwanted causes of variation. Okay, unwanted causes of variation. The essence of statistical process control is to ensure that the output of a process is random so that future output will also be random. So you're doing sampling of a statistical process to make sure that your samples are random, and so that when you do find defects, you know that there is a true process problem. There's 4 key steps in statistical process control. That's measuring the process, and when a change is indicated, find the assignable cause. An assignable cause is a known error. Okay, an assignable cause is a known error. The next step is to eliminate or incorporate the cause. The 4th step is to restart and revise the process. So again, going back to that whole assignable cause, we're going to talk more about some of the different causes in the next couple slides, but an assignable cause in a process is, let's say I'm walking through a manufacturing facility and I run into one of the machines that is building our products, and I throw it out of alignment. That is an assignable cause. I messed up that machine. Let's say an employee who is working on making French fries, and they've got the little salt shaker, and the top falls off of the salt shaker, and so there's a ton of salt in that batch of fries. That's an assignable cause. The process is still in control, but there was an assignable cause on why that batch or that process wasn't in control at that moment. You know what the cause is. It's a known error, so it's an assignable cause. So this slide's got a lot of meat to it. There's various process control procedures and definitions. So process control is concerned with monitoring quality while the product or service is being produced. Okay, so process control is making sure that your process is running smoothly, and if it's not, that you catch things while you are still producing them. Statistical process control is testing a sample of output to determine if the process is producing items within a pre-selected range. Okay, so statistical process control, you're taking a sample of the output to make sure that that process is running smoothly. So as an example, this Yeti mug that I'm drinking out of, okay, they make thousands of these per day, probably. They do not inspect thousands of these per day. What they do is they probably inspect one out of every couple hundred. They pull it off the manufacturing line, the assembly line that's making these mugs, and they'll pull one off every once in a while, and they will test it. It's a sample. It's a random selection of products to make sure that they are still meeting their required specifications. So that is statistical process control. They are not inspecting every single one of these, because if the process is in control, then they don't have to. They don't have to waste the time testing thousands of mugs every single day. If the process is in control, then they know that things are running smoothly. So that's statistical process control. Control charts are run charts to which there's two horizontal lines. They're called the control limits. They're added to monitor process output to see if it's random. So we talked about this a little bit in the last lecture recording, that with control charts, you've got your upper control limit and you've got your lower control limit. And as long as the process output is within that range and close to the process mean, then your process is in control. When you start to get data points that are above the upper control limit or lower than the lower control limit, then your process is out of control. And hopefully it's just an assignable cause or a known cause. Otherwise, you have a process problem that you need to address. Control limits are statistically, they're chosen statistically to provide a high probability that the points will fall between these limits if the process is in control. So you do not just randomly pick your upper control limit and your lower control limit. You statistically calculate out what your upper control limit and your lower control limit are, and we will go over that in some of the following lectures. When we talk about system stability, a system is stable if it's governed by only common causes. So there is going to be some variation in many processes that is acceptable and tolerable. And those are common causes and they're okay. So that is a stable system. An in-control system is when there's no special causes that affect the output of a process. And an out-of-control process is when special causes are present in the process. Okay, so assignable causes are known and they're not okay, but you can correct them and you know that your process is still in control. If you have special causes, that would make your process become out of control. So let's look at a control chart again. You can see that there is some normal variation in between the upper control limit and the lower control limit, and that normal variation due to chance is acceptable. So this process, if it didn't have that 13th or 14th data point out of control, most of that variation is acceptable. But you've got that one outlier that's above the upper control limit. It is out of control. So unless it's an assignable cause, then this process is out of control. So let's think of an example and why it's okay to not always be exactly at that mean. Think about a bag of potato chips. They say the bag of potato chips is going to weigh about a certain amount. It's extremely hard for that manufacturer to be perfect every time with the weight of the contents in that bag of chips. Some normal variation is acceptable to them as long as it falls within the upper control limit and the lower control limit. What they don't want to do is give you a tiny little bag of chips that weighs 3 pounds above the upper control limit. They also don't want to give you a bag of chips that's empty and doesn't weigh anything. It's just full of air. So that would be two extreme examples of an out of control process. But some variation right here, some normal variation that's close to the mean, that is acceptable, and that process would have been in control if it weren't for this outlier, which makes the entire process out of control. So variation, let's talk about variation real quick. Processes usually exhibit some variation in their output. Common or natural variation is variation that's inherent in the process itself, okay? And that is generally acceptable variation. Assignable variation is variation that's caused by factors that can be identified and managed. It is generally accepted that as variation is reduced, quality is improved. That was a big thing for Deming. He really focused on reducing the variation in processes as a source for improving quality. So Deming really worked on reducing variation. So humor me for a second. Take out a pen or a pencil and a piece of paper. And we're not going to write this out 9 or 10 times, but really quickly, use your primary hand and write the first letter of your name. Do it 4 times. Now, put it in your other hand. So if you're right-handed, now put it in your left hand and write your first initial of your name 4 times. You're going to find, first of all, it's a lot harder, but you probably are going to be pretty consistent even with your left hand or your secondary hand. So if you look at what you wrote down on that piece of paper, there is a little bit of variation when you used your primary hand. That's common caused variation using your normal hand. When you use your secondary hand or your non-dominant hand and you did a couple of those letters, they also had variation using your other hand, but it's also common cause. They look about the same. Now, if you were to try and write your first initial of your name twice with your primary hand and twice with your other hand, what you'd get is 2 letters that look about the same, and then you'd get 2 letters that look about the same, but there's variation there. The difference with this process is that when we changed from normal to the other hand, that is assignable variation. We know why the variation occurred between the first 2 letters and the second 2 letters because you changed hands. That is a overly dramatic way of trying to explain variation by using your handwriting with your primary hand and your less dominant hand. But that is common cause variation. There's a little bit of variation when you use your primary hand. There's a little bit of variation when you use your other hand. But when you put those 2 together, back to back, you see the change from one hand to the next. That's assignable variation. Okay, now let's construct control charts. There's the steps to constructing a control chart. And what we're going to learn in the next couple lecture recordings is how to create the various different kinds of charts, the X charts, the P charts, the C charts, the 4 different ones that we're going to learn. You follow these steps no matter which kind of chart that we're creating. So first you're going to prepare. So choose the metric to be monitored, determine the basis, the size, and the frequency of the sampling, and you set up your control chart. Next, you're going to collect your data, you're going to record it, you're going to calculate the relevant statistics, whether it's an average, a range, or proportion, and so on. Then you're going to plot the statistics onto the chart. Step 3, you're going to determine the trial control limits. So draw the center line, which is your process average or your mean, onto your chart. You're going to compute your upper and your lower control limits. Step 4 is analyze and interpret the data. Investigate the chart for lack of control. Eliminate any out of control points and recompute control limits if necessary. So you're going to essentially do a trial and error. You're going to analyze it, interpret it, and see if it's a good chart. Number 5, you're going to use as a problem solving tool. So continue data collection and the plotting. Identify out of control situations and take corrective action. Okay, so you'll take corrective action when you determine that your process is out of control. And then step 6 is determination of process capability using the control chart data. So you're going to see, based off of all your data, if your process is in control or if it's not in control, and then you'll take those corrective actions to make sure that you can get your process into control. So for the quality metrics, there's 2 different kinds of control chart classifications. The first one is a continuous metric. This is one that can be calculated from data that is measured as the degree of conformance to a specification on a continuous scale of measurement. So examples could be length, volume, weight, height, time, color, sound. Those are all things that can be measured. So you would use an X bar or an R bar chart for continuous metrics. Your discrete metric is one that is calculated from data that is counted. Okay? Examples would be number of flaws, years, accidents, students, satisfied or dissatisfied, good or bad. And in many of the questions that I give you on your quizzes and exams, I will not tell you which chart to use. But you're going to have to determine whether it's something that is counted or whether it's something that is measured by the data that I provide to you. So for discrete metrics, you'll use either a P chart or a C chart. For continuous metrics, you'll use either an X bar or an R chart. And so you'll see this chart again. This is the control chart classification. Your control chart is what you're going to make. If it's a continuous metric where it's measured, you will use an X bar chart, which detects a shift of the mean. So a shift of the mean means your average is changing either lower or higher. Generally what I see is exam number 1 is pretty good, exam number 2 is a little bit harder, so I detect a shift of the mean because the averages are getting worse from test 1 to test 2. So that would be a mean chart or an X bar chart. Another continuous metric would be a range chart. This detects the shift of dispersion. So are things getting higher or are things getting lower? Are things getting heavier or are they getting lighter? These are things that are measured. Next are our discrete metrics. These are things that can be counted. So if you'll use a P chart for fraction defectives. So what's your defective number? And for C charts, it would be the count or the number of defects. So those are the discrete metrics that you would use when something is counted. So our next couple videos are going to be, one will be on continuous metrics. So we will walk through how to do an X bar chart and an R chart. And then the video after that will be discrete metrics, and that'll be your P chart and your C chart.